This is a video about Scalpel, a language based on FNets. It supposes you're already sold on the advantages of FNets, the portable efficiency across high and low latency platforms, the formality and improved correctness of programs, preservation of sequential language semantics, and the other things that we talked about in the last video. But it also supposes you also recognize the need for real programming features, things like reusability, top-down programming, modules with behavior more flexible than the tactics have, first-class modules, templates, arrays, data parallelism, dynamic memory allocation, dynamic linking, object-oriented programming, class-based, that is. And this is where Scalpel comes to the rescue. So Scalpel stands for Scalable Planning Language. A computer program is a kind of a plan, and that's the only kind of plan we'll talk about here. But Scalable Planning Language can theoretically be applied to all kinds of different planning issues. Scalpel is a visual language built upon the same basic principles as FNets, so we'll jump right in and you'll recognize how things work right away, and we won't go over that again. It has a similar visual notation, but the terminology is a little bit different. So this video will introduce Scalpel constructs and motivations. It's not going to fully describe the language. It's mostly going to tell you how we address all of the goals that we just outlined by introducing some constructs into the normal FNet framework. So in Scalpel terminology, a network is called a strategy rather than an FNet. So we won't really use the term FNet anymore. We'll refer to strategies for the networks of circles, rectangles, lines. In the previous video, in an FNet, we called a circle a tactic. In Scalpel, a circle in a strategy is called a context. It's where a tactic executes, but the tactic itself is considered as a separate entity that sort of plugs into the context. The idea is that this allows a single tactic to be used in different contexts without re-implementing it, and this is to the end goal of reuse. The word plan in Scalpel will refer to either a strategy or a tactic. So often we'll refer specifically to strategies or tactics, but sometimes we'll refer to plans, which means either one will do in that context, so to speak. So how do we get it so that a tactic can go into different contexts? Well, obviously we can't have the tactic referring specifically to resources and or the control states on those resources. So we parameterize those. Instead of talking about resources within a tactic, it refers to roles, that is, the role that those resources play within the tactic. And instead of referring to the control states of those roles, we refer to the transitions of those roles. That is to say, the tactic will perform transitions to the roles, and that will result in new control states occurring to the resources that play those roles. The context that the tactic fits into and the adjoining notation specify the bindings for these roles and transitions. So for example, the line that goes between the circle and the rectangle, between the context and the resource, will be labeled for a role of the tactic, and it's called the role binding. Very simply, it tells which resource that role is representing. Shorthand, if the resource itself has a label and the role bindings, some of the role bindings do not have a label, the role bindings will just borrow the label from the resource. Then remember that within the rectangle, right next to where the line joins, there are new color dots that tell what colors that tactic might change that resource to, what control states. In this case, those new color dots are labeled with transition names, and they're called transition bindings. So in other words, if the tactic performs transition X to role A, it will follow the line for role A and look for the colored dot with labeled X, and will change the control state of that resource to that color or that control state. Remember also that these lines, which are now called role bindings, have arrowheads on them. And we now call those arrowheads permissions. If you recall, the permissions were observe if it has one arrowhead on the context or circle end, replace if it has one arrowhead on the rectangle or resource end, update if it has arrows on both ends. We can also call that observe replace. It's exactly the same thing. And no data if it has arrows on neither end. Similarly, the roles within the tactic have usages that are exactly the same. That is, that's how the tactic is actually going to use that role. So these permissions have to allow for any usages that the tactic wants to have on that role. In other words, the role usages have to fit within the role binding permissions. Now usually the role and transition bindings on the context must match exactly in name and number to the roles of the tactic, the roles and transitions. And that makes sense. If you're going to stick a tactic into a context, you'd better hope that all of the roles get bound and all of the transitions get bound and that no extras get bound. But as it turns out, you can bind some extra role bindings. They're called empty role bindings. These are allowed even to further reuse by allowing you to put a tactic into a context that you really wanted to have one or two more sensor roles. That is, you needed a role to tip off another resource whenever this tactic fired. Or you needed another resource to keep this tactic from firing except for under certain circumstances. So these empty role bindings have very specific requirements. Their name must start with an underscore. That's what tips off the system that these are empty role bindings, and that they're not required to match a role within the tactic. They must also be predictable and have just one transition name done. And that's exactly how they do their job. Because they're a role binding, they will keep the tactic from firing until the associated resource is ready, has the proper control state matching the access dot on this empty role binding. And because it's predictable, the transition will be performed whether or not the tactic within the context actually performs a transition to that role. And it won't, because it doesn't even know the role exists, the role binding exists. So that done transition will be eventually performed. And that's how these empty role bindings are allowed to go onto any context. So earlier we said that both tactics and strategies could be referred to as plans. And as it turns out, any plan can go into a context, including another strategy. In that case, we essentially have a parent strategy and then a child strategy within a context in that parent. In order to make that happen, the child strategy also has to have roles and transitions in order to make it so that the parent context can bind those to resources in the parent. The way that happens is that within the child, each role is represented by a formal resource, which looks just like a normal resource, rectangle, except that on the right side of the rectangle, it has a small triangle and a small box called a transition box. The formal resource is named for the role that it represents. And uniquely colored dots in the transition box are labeled for its transitions, uniquely colored relative to that resource. So role bindings in the parent associate the formal resources, that is the roles, in the child with actual resources in the parent. So every one of these formal resources in the child is associated with a role, and that role is associated with the role binding on the context in the parent, and that role binding associates that role and therefore that formal resource with another resource in the parent, which we'll call the corresponding actual resource. So they will share content state. But how does the control state work? Well, under proper circumstances, when the role binding in the parent is ready, in other words, matches one of the access dots on that role binding for that resource, the control state is stolen from the actual resource in the parent to become the initial green control state of the formal in the child. So again, if we think about control states as colored tokens, that colored token is taken away from the resource in the parent, and a green token is placed on the formal resource in the child. The exact circumstances under which that happens are a little bit beyond the context of this talk, but they're very flexible. At that time, the child can access that formal resource just as always, transitioning that control state over and over and over again, and the parent never sees that control state back on the actual until, in the child, the color of the formal resource changes to the color of one of those transition dots in the transition box. And at that time, the transition name associated with that color is taken as the transition that will be performed to that role. And that transition name, not color, just name, is then brought back to the parent to that associated role binding, and that transition is issued to that role binding, and therefore it is looked up in the transition binding for that resource. That name is, and the associated color is then associated to that, is then assigned to that resource. The somewhat confusing part of this is colors in the child are completely independent from colors in the parent. Only the name, transition name, is moving from the child to the parent. So that moves the control state from the child resource back to the parent resource. The child can also be made to finish, and that means no longer can any of the formal resources in the child ever get an initial control state again. But they can still produce transitions back to the parent. So they can move control states back to the actual resources in the parent. So after a child has finished, there's a very orderly process that it can take, and it can take time, but it doesn't matter. Logically, it has finished right then, and I won't go into that right now. But eventually, all of the control states can move back to the parent. And in fact, the child can finish instantly, atomically, as soon as it has absorbed all the control states from all of the formal resources, in which case it acts very much like a tactic does. That is, when it fires, it takes all of the control states away from the resources in the parent. It does its thing without the parent understanding what's going on necessarily, and then returns the control states one by one back to the parent. And when it's all done, since the formal resources in the child cannot turn green again, they're completely inaccessible, so the child has no access to anything outside of itself. It can be garbage collected, and it can be made to start again anew with new resources. So again, just like a tactic, it can be stateless. And there are many varieties of ways that you can handle this within ScalPL to any degree of modularity. So that's nice in itself that we can stick one plan into another, whether it's a tactic or a strategy, into a context in another plan. But instead of labeling these contexts with the plan to execute there, we can also have the context obtain the plan from a resource using a $plan role binding. So the $plan role binding is on the context, it goes to a resource, and that resource actually holds a plan. The context itself, not the thing in the context, but the context itself looks at the $plan role, and when it's ready, and if it finds a plan there, it can read it and plug it into the context and then execute that plan. As a matter of fact, even when you label a context with a name of a plan, that's really just a shorthand. It assigns that plan to a resource, and then it attaches a dollar plan role from the context to that resource. So again, the dollar plan role belongs to the context itself, not to the plan that executes within the context. And object-oriented constructs, will use this later, we'll get into that, but even before that, you can see that, for example, if you put a dollar plan role onto a formal resource, that you could be passing plans from the parent into the child for the child to plug into contexts within the child. So if the child could be considered a template or a pattern that takes as arguments, as roles, other plans that it will plug into the right place within itself to accomplish what the template or pattern is supposed to accomplish. You can also think of this dollar plan facility as being used for dynamic linking, or any number of combinations of those things. So basically, plans are first-class objects. They can be stored on resources. ScalPL also has arrays, resource arrays. So any resource can have any number of dimensions. Each dimension, it's usually like 5 or less. Each dimension is shown as a hash mark on the left side of the rectangle. So the rectangles we've been showing so far haven't had any hash marks. They're zero-dimensional or scalar. They're both the same thing. If it had one hash mark, one-dimensional, two hash marks, two-dimensional, etc. Each dimension has an index domain, that is the kind of indices that that dimension will take. And the default is integers. Not positive integers, not a range of integers, but the entire integers. So these index domains are often infinite, and as a result, resource arrays by default have an infinite number of elements in them, which sounds somewhat problematic. It turns out not to be problematic at all, in part because of control state. If the index domains are ordered, then you have a little bit more control in that you can talk about ranges, for example, of indices in that dimension. So each element of one of these resource arrays is uniquely addressed by one index in each dimension from the index domain of that dimension. There's no implied spatial relationships between different elements of the array, just like there's no implied spatial relationship between any two resources in ScalPL or FNets. Each element has its own content and control state. So they're like completely different resources, except they all share the same domains, that is content and control domains. So, if it's an array of integers, every element is going to be an integer. In order to bind these resource arrays to contexts, we have to have role arrays and role binding arrays, and we do. An array role binding looks just the same as our previous role binding. It's still just a line. The size and dimensionality of the role binding is determined by what it's bound to. If it's bound to a one-dimensional array, then it's a one-dimensional array role binding, and it binds a one-dimensional role array. And by default, the elements bind one-to-one. So if there's just the line between the context and the array, the elements are going to bind one-to-one and have the same dimensionality as the array. But you can also add binding modifiers to control which resource elements to bind to, and the dimensionality of the role array, which is being bound to those elements, and the correspondence between the roles and the resources indices. So let's get into those a little bit more. A binding modifier is a set of binding rules that will tell how the contents of some primary roles on that context will be used to constrain the binding of a secondary role to elements or an element of a resource array on that context. So basically, we're going to name some of the role bindings on that context as primary role bindings. And those role bindings might be used for nothing other than to help index that secondary role binding to help it point to certain elements of the array. Or, the tactic within the context may also use those primary role bindings for its own roles. But the primary role bindings may be empty role bindings. So we'll get to that. So the plan in the context, when it looks at that secondary role, it sees the secondary role. It doesn't necessarily see the array resource on the other end. So if we're just binding to one element of the resource, it's going to see a scalar secondary role. Most binding modifiers are represented by arrows within the context circle, labeled with rules. From the primary role bindings, which may be empty as I said, to the secondary role binding, there will be the context circle, and there will be arrows within the context circle going from the primary role bindings to the secondary role binding, and each of those arrows will be labeled with binding rules. The binding modifiers are evaluated by the context itself, and all bindings are made atomically and before the plan within the context is initiated. So the tactic or plan of any kind inside the context doesn't care that these are present, and it doesn't know that they are present. All it knows is that when it starts, all of its roles have been bound. That means that the context has to do some fancy stuff sometimes. It has to be looking at the primary roles as soon as they become ready and see if the things indexed by those primary roles on the secondary role are ready. And if they're not, and the primary roles become unready again, then it has to start all over again, etc. It may have to do some backtracking, etc. But the context guarantees that once it initiates the tactic or other plan within the context, all of the roles will have been bound. So examples of what these binding modifiers can help to do, that is the rules on the binding modifiers, they allow the secondary role to, for example, bind to just one element or one vector or one plane of a larger dimensional resource array, sometimes called a section. Bind to a range of indices or a set of indices within that array, to shift indices relative to the resource, permute the indices relative to the resource. So you can actually say, this resource is 10 by 20, but I want the tactic or plan within the context to see it as a 20 by 10 instead. So I want it to use the second index as the first and the first as the second. It can bind to and reference elements indirectly through an array on the primary role binding. So in that case, for example, the tactic or plan can say, I want to access element 10, 20 on the secondary. And the context can say, wait, I'm going to take that 10, 20, and I'm going to instead access an array on the primary, look up the index in that element, and use that index or address to actually address the secondary array. So all this happens behind the scenes. The plan within the context doesn't see any of this happening, and it doesn't care. All it knows is that it's got certain roles that are bound to certain elements, and that it's accessing those. And that's actually a very good thing and makes things very reusable. Now another factor about these resource arrays, so they're usually infinite by default. You can specifically say in portions, every access to this array is now going to be limited into this range. And therefore, the runtime system can say, fine, now I can just allocate that many elements all next to each other maybe, or they might be on completely different processors. And I don't have to worry about going outside that range. I know how big the array is. But by default, the arrays are infinite, and just changing an element from its initial state effectively allocates it, if not already. That is, you're essentially saying, okay, I'm accessing this element of the array now. As soon as you index it, You put something into it and you change the control state, and now the runtime system is keeping track of the content and control state of that element. Sometimes changing its control state back to the initial control state will effectively deallocate it. And that is if all accesses to that array element to the initial control state will always be a replacement, always have replacement permission, then there's no reason to keep the old content state around in that case. If it's in its initial control state, you know that its content state is going to be overwritten, so the runtime will just deallocate it. But what about data parallelism? In that case, you want to have many different accesses occurring all at one time. And that means essentially you have to have many different contexts accessing the array at one time, and the number of contexts has to scale with the size of the array. For that, ScalPL uses something called a dupe, which it means duplicate. A context can have, you can mark one or more role bindings on a context as dupe bindings by putting an asterisk or a plus next to them. And what that means is that before the context fires something in that context, it will look at those role bindings and expect to find a number or a range of numbers, integers. It will replace that one context with that many different contexts, and it will assign each one of those contexts a different element of that range of numbers. So fine, now when we had a context, it was pointed to a resource with a 20 on it, with one of these dupe bindings. Before it fires, the context will replace itself with 20 different contexts. One will get a 1, one will get a 2, one will get a 3, one will see a 3, one will see a 4, etc. on that roll. And what do these contexts do? Well, typically they use that role as a primary role to index a secondary role binding that is attached to an array resource. And that allows each one of these different contexts to be accessing different parts of a larger array. Now these different copies, which we call replicants, can be coordinated so that they all have to finish doing what they're doing before they can all start up again, or they can be uncoordinated so that each one can operate completely independently of the others. That's called dupe all and dupe any. Moving on to object-oriented programming, we already said we're helped by this $plan role that will allow a plan of any kind to be read off of a resource and plugged into a context. Typically, a strategy already encapsulates data, that is its resources, and behavior, that is the context inside of it with plans, through a well-defined interface, that is the roles with transitions. So a strategy already kind of serves as a good start for object-oriented programming. A class strategy, that is, if we want to use a strategy as a class, will need a few extra features. First of all, we'll add some things called instantiation levels on resources. So if the strategy represents a class, then this will allow instances of that class or objects with their own persistent state to be created and carried from context to context. Then we'll add binding constraints, and that will basically allow us to create so-called methods. It allows roles to be associated with methods rather than with the entire strategy as a whole. And then as far as inheritance and class hierarchy, inheritance will be handled through delegation. The class hierarchy is more of a type system. So first, the resource instantiation. Normally, when a strategy starts in a context, the director, that is the thing that's making this all go, if you remember from FNets, kind of the overseer, instantiates the resources of that strategy. until it finishes. Now, by instantiates, it means it finds a spot to store the content and control state for each of the resources on the strategy. And we'd like to consider that it then records that location on each rectangle. It says, okay, for this resource, the content and control state's stored over there, and on this one, the content and control state's stored over there. But for a class instance, we actually want the state and these markings on these rectangles to hang around for the resources so that we can allocate the space for these resources, their content and control state. Then later on, when we take the same strategy and plug it into a different context, we'd like it to use those same ones. That way we can think of this strategy as a class instance, as an object. It now has persistent state that it carries with it from place to place, and whenever we stick this strategy into a context, it all points off to the same state, which is the content state and control state of its resources. So to do this, we give these resources what's called instantiation levels. Any resource or context can have an instantiation level, which is shown as a number of shadows behind the resource rectangle or the context circle. So if it has no extra shadows, it has instantiation level 0, and that's all of the resources and contexts that we've been seeing so far. A context with an instantiation level greater than 0, that has at least one shadow, also has a $O plan role. Now remember, they always have this $plan role, even though it might be hidden by just labeling it. But now, if they have at least one shadow, they'll also have a $O plan role. So if the context has an instantiation level greater than 0, it will instantiate all the resources on the plan with having that same instantiation level as itself. So if the context has instantiation level 1, it will instantiate, that is, find a place to store all of the resources that also have instantiation level 1, and it will mark the rectangles with where those are stored. And it will then take that marked up strategy before it's even started it up, and it will replace it out to the $O plan role. And then the context will bind all or any formal resources having the same instantiation level as itself. So if there are any formal resources of instantiation level 1, it will bind those and then execute it as it normally would. Now often, there won't be any formal resources with instantiation level 1, so it will have finished its job just as soon as it has instantiated all of the IL1 resources and it has written that new strategy out to the $O plan role. So what has it done there? It has created an instance of the class. If we took that same strategy and ran this level 1 context on it again and created a different thing on the O plan role, it would be a separate instance of that same class. And each of them, when we put them into contexts, in different contexts, each one would access their own instantiated resources and not the instantiated resource of the other. So what about class resources? Sometimes we want the class itself to have state that gets updated. For example, every time we create a new object, we might want to give the object a serial number or something. And that's fine too. We just create instantiation level 2 resources and an instantiation level 2 context. And therefore, when we instantiate the instantiation level 2 strategy, it will instantiate the instantiation level 2 resources, which will now become class resources, and put that to its $O plan. And then it will still have instantiation level 1 resources that have not been instantiated yet. So the thing that has just been written will now be a class with some state. And then we can now instantiate that into different instances of the class or objects. You could theoretically go higher, instantiation level 3, instantiation level 4, etc. And there are some weird cases where that is useful, but not every case. So now we are able to have these strategies carry their state around with them and plug them into different contexts, etc. The one big problem is that, remember, the rule is that when you stick a plan into a context, the context has to bind all of the roles of the plan. And in this case, we're going to have the plan represents a class or a class instance, and we're not going to want to bind all of the roles generally. We're going to want to invoke a method on that object. In ScalPL, there aren't specifically things called methods, but instead there are ways to specify that you only want to bind certain roles. We do that through things called binding constraints. So a binding constraint is a logical expression on role bindings that you associate with a strategy, and it basically says you can bind this role and this role and this role, or you can bind this role and this role and this role, or you can bind, etc., in that kind of a logical expression. So that when that strategy is put into a context, as long as the binding constraint is satisfied, then that's okay. So where do methods come in? Methods are just extra role bindings. So basically, if you are intending to use method XX of this class instance, then you will add an extra role binding that specifies that you want to be using method XX. And the binding constraint will say, oh, he wants to use method XX, that means that I also have to have these other roles bound, but no other roles should be bound. So methods are actually just kind of a higher level imaginary construct within ScalPL, but they work the way you would expect them to work. Now, as far as creating some classes from other classes, ScalPL uses just standard delegation for that. That is, what it really does is it includes a context in one class that has another class inside of it. So you have a parent class inside of a subclass. And any time the subclass wants to handle extra functionality, it can. That is, if the roles are bound on the subclass can provide context bound to those roles that will do the right thing. However, if that functionality should be handled by the parent class, it simply reroutes those roles bindings that are coming in to the context within itself that holds the parent class. There are a few tricks to this, and one of the tricks is making sure that the parent class gets instantiated at the same times and at the same frequency that the subclass is instantiated at. And the other issue is having wildcards or other ways of saying, okay, all of the things that the subclass isn't handling should go to the parent class. And for that, a construct called role sets is available, and role binding sets. A role binding set is just a set of role bindings. So you can actually just say, give me all of the elements of this role set that I have not referred to otherwise. And that is obviously useful when you want to say, take all of the role bindings to me that I haven't handled and route them to my parent class. Now, class hierarchy is a little bit different in that that's more something that happens in the type system, and it is present in the type system, but there also has to be some assurance the subclass can handle anything the parent can handle. And the subclass can be used anywhere that the parent is used. So there are some assurances within the type checking system. So that's it in a nutshell. That's ScalPL. That's the way that it provides for top-down programming. So the top-down programming is handled through the ability to put networks within, strategies within strategies within strategies. You can make your high-level strategy with these contexts that you don't really know the specifics. You just know in general they're going to behave like this, and that behavior could be very complex. And you can work down to the point that the behavior within those contexts is very specific, all the way down to the behavior of a tactic. The ability to be piping in fact, these role sets, actually, it turns out, are very convenient as libraries as well. They're hierarchical, just like a library has to be. You can access just certain elements within them without requiring to know what the other elements are. So you can treat those as libraries. We now have patterns, we have templates, we have object-oriented and class-based programming. We have data parallelism, we have dynamic memory allocation, we have dynamic linking, and more. All while preserving the advantages of FNet. Still have all of those: portable efficiency, improved correctness, preservation of sequential semantics for the tactics, etc. So this seems like a superior basis for exascale programming, especially since you're not dealing with placement or what kind of latency you're dealing with at all while you're actually setting up the program or the algorithm. That can all be optimized after the fact, maybe at runtime. And that also includes checkpointing. The checkpointing can be optimized based on FNet's properties of which parts are deterministic and therefore can be re-executed with the same results. And therefore, if we record certain state, content state, and control state at certain places during the execution, if something goes wrong, we can re-execute from that point, etc. So, this just seems to be definitely worth investigating further. Compare it with most any other solution for parallel programming and exascale programming. I'm not saying that this is finished, that it's ready to go. It's not. Much work's left to be done. Even on refining and extending some of these concepts and principles, and building a proper ecosystem to get much more information on what I've talked about today. You can see my book called Scalable Planning by David DiNucci, written in 2012, I believe, and it will go into great depth in all of these issues, and a great deal of theory if you want to go there, and a great deal about how to implement this stuff efficiently if you want to go there. So thank you.